Dear students, in this lecture we will proceed the applications of derivatives. In the previous lecture we have discussed how could we find the local maxima and minima, which is the most important topic regarding applications of derivatives. And this lecture will further extend that topic and note that what are the further applications of derivatives. There are many applications of derivatives, but few of them will be studied in your course, and that is the last one. We are studying in this lecture that what is concavity, point of inflection, and Lopital's rule. Remember that this H is silent here. We pronounce this as Lopital's rule. So first of all, we will study here that how could we know that a graph of a function is concave up or down. So the graph, just look at this figure. In this figure we see that we observe that this is the whole graph of the function, and this portion opens downward and this portion of the graph opens upward. So that portion which opens downward is said to be concave down, and that portion which opens upward is said to be concave up. This is the graph of the function y is equal to x cube. We see that if we draw here in this portion, the portion which is concave down, if we draw tangents on each point of this curve, this tangent has maximum slope. It means that f prime is maximum, because f prime is the slope of tangent line. So the slope of this tangent line is maximum because this angle is maximum. Whenever we go forward, that is the second tangent. Now this second tangent has angle less than this angle. So the slope of this tangent line is less than the slope of this tangent line. If we then go forward and take another point on this graph and draw a tangent line, so we observe that this third tangent line has minimum slope. Similarly, if you go forward here and draw another tangent, that tangent has lesser slope than the rest of all those. So it means that if we go forward on this graph and draw tangents, so the slope of all those tangents decreases. It means that f prime decreases. So whenever the portion of the graph is concave down, then in that case the derivative of the function will be decreasing in that portion. Similarly, if you look at this portion is concave up. So if you take this point and draw a tangent line, so this tangent line has this slope. If you go there and draw another tangent line, so the angle of this tangent line with the x-axis is greater than the angle of the previous one. So it means that if you go forward, then the angle of all those tangents increases when you go forward along this curve, along this portion of the graph which is concave up. So it means that the derivative of the function increases in that portion of the graph which is concave up. So that is the definition. The graph of a differentiable function y is equal to f of x is said to be concave up on an open interval I. Just look at this portion. this portion starts from for this value of x and ends at here. So in that case, in this interval this graph is concave down. So in that case, the interval I is here, starts from here and ends at there. So a graph of a function is said to be concave up if f prime is increasing on I. Concave up. If f prime is increasing, then we say that that portion of the graph is concave up in that interval, in these values of x. And whenever f prime decreases in some interval, then we say that the graph of the function is concave down. So that is the definition of concavity, concave down and concave up. So here is a test, second derivative test for concavity. That is the second derivative test. Let's say a function is twice differentiable. It means that you can find the second derivative of the function on some interval I. So whenever, if you see f double prime, and the answer of f double prime for all those values of x in the interval positive, if f double prime is positive on the interval I, then we say that the function is concave up. And whenever the second derivative of the function is negative on the interval I, then we say that the graph of the function is concave down. Just look at this figure. We see here that this whole graph is concave up. Concave up. So that is concave up. Just look at this, all these tangent lines. Whenever you come, you start from here, you take a point from there and draw a tangent line. So tangent line has a negative slope, because this angle is greater than 90 degrees. All these angles are greater than 90 degrees. So whenever you go forward and draw tangents and that is expect, we see that the graph is concave up. So it means that f prime will be increasing. So whenever f prime is increasing, you see that all those tangent lines has slope which is increasing from -2 to +2. So f prime is increasing. So whenever a function is increasing, its derivative will be positive in that interval. We say that a function f is increasing whenever the derivative of the function is positive in that interval. In that case, in this case, we see that f prime is increasing because this is concave up portion, and concave up portion f prime is increasing function. So whenever f prime is increasing, its derivative will be greater than 0. The derivative of this f prime will be greater than 0. So that is how we write here if y double prime will be greater than 0, because y prime is increasing. So the derivative of y prime, which is actually y double prime, will be greater than 0. So y double prime for concave up portion will be greater than 0. And similarly, if you take concave down portion, now in concave down portion, we see here that the derivative of the function decreases. So whenever f prime is a decreasing function, so for a decreasing function, the derivative of the function will be less than 0. Now here f prime is itself a function, so whenever f prime is decreasing, its derivative will be less than 0, negative. So the derivative of f prime is actually f double prime. So for concave down portion, f double prime will be less than 0. So that is how it is written here, that whenever f double prime is greater than 0, double prime is greater than 0, then we say that the graph of the function is concave up. And whenever f double prime is less than 0, then we say that the graph of the function over the interval, the values of x over the interval I, is concave down. So that is the second derivative test to check the concavity of a function, that whether the function is concave up or concave down. Whenever the second derivative is positive, then we say that the function graph is concave up, and whenever the second derivative is negative, then we say that the graph of the function is concave down. The third one is point of inflection. Point of inflection. Just look at this point. This point divides this whole curve into two portions, namely concave down and concave up. So that point which divides a curve into two portions, that is concave down and concave up, that point is called point of inflection. So that is written here. A point which divides a curve into two portions, that is concave up and concave down, it is said to be point of inflection. And we say that for concave up portion of the graph, y double prime second derivative of the function is positive, and for concave down second derivative is negative. So second derivative is negative, second derivative is positive, and at point of inflection second derivative will be equal to 0. So whenever you check whether the function is concave up or concave down, and whenever you want to find the point of inflection, all those rules will be followed, the second derivative rule. Now how to check the point of inflection, how to find the point of inflection of a graph? So that is the criterion which is presented here in front of you. First of all, a function will be given to you, and you need to find the second derivative of the function. So first of all, find the second derivative of the function, and secondly, put that second derivative equal to 0 or infinity, undefined, to get the values of x where inflection is expected. Whenever you put f double prime x equal to 0 or f double prime x equal to infinity, to get the values of x, those values of x for which the inflection is expected. We put f double prime x equal to infinity whenever you are given a rational function that is discussed in the previous lecture. Anyways, so put f double prime equal to 0 or infinity to get the values of x for which there is inflection. Now how could we know that value of x is associated with the point of inflection? We will take two values from left to right of this x. The value of x which is obtained by putting f double prime x equal to 0 or f double prime x equal to infinity, we will take two values of x from left to right of that x, and we will put, whenever you put those two values of x and the second derivative of the function f double prime, and you see that f double prime changes its sign because at point of inflection one side is concave up and the second side is concave down, and whenever a function is concave down at one side, then the second derivative is negative, and whenever the graph of the function is concave up, then second derivative will be considered as positive. So and at point of inflection, if the second derivative of the function is 0, so whenever you put two values of x from left to right of that x and second derivative of the function, then at one side second derivative will be negative, and at second side second derivative will be positive, because at one side the graph is concave down and at second side the graph is concave up. So whenever there is a change of sign in the second derivative of the function, then we say that that value of x which is obtained here is associated with point of inflection. Here is an example. The example is find the point of inflection for y is equal to x cube minus 3x plus 3 if any. If possible, then find point of inflection. There is a cubic function, so follow those steps. We will follow those steps. First of all, we are given this function. So function is given to us, f of x, or you may say y. We need to find the second derivative of this function. So that is the first derivative of this function, which is 3x square minus 3, and differentiate again to get the second derivative of this function. Second derivative by using power rule, 3 2s are 6x, and the derivative of 3 is 0, so 6x. It means that the second derivative of y is 6x. So that is the first step, that we have obtained second derivative of the function. Now secondly, we need to put f double prime. We need to put this second derivative equal to 0 or infinity. We see here that this second derivative is not inflection, is not a rational function, that is a polynomial function. So we'll only put this second derivative equal to 0. So put for possible point of inflection, put y double prime second derivative equal to 0. Second derivative equal to 0 means 6 equal to 0, dividing by 6 to get x equal to 0. So that is the value of x at which inflection is expected. So that is x equal to 0. We need to take two values of x from left to right of this x. So just look at here. Take two values from left to right of x equal to 0. That is x equal to 0. Left side value is minus 1 and right side value is plus 1. You can take the nearest value at the left side, minus 0.1 or minus 0.2 or minus 0.5. You can take any value here, and similarly you can take here plus 0.1, plus 0.2, and so on. So I have taken minus 1 and plus 1. So we need to put these two values, minus 1 and 1, in the second derivative. So put x equal to minus 1 in this second derivative. Y double prime is equal to 6x. So whenever we put x equal to minus 1 in this second derivative, so 6 into minus 1 is minus 6, and minus 6 is negative. Now put x equal to 1 in the second derivative. So whenever you put x equal to 1 in this equation, we'll get plus 6, so that is positive. So see here that y double prime, or we may say that f double prime, changes its sign. That is negative and this is positive. So y double prime changes its sign, so it means that there is inflection at x equal to 0. So that is how to find point of inflection. And the for the point of inflection, we need to find the point on the curve, and the point on the curve is in ordered pair. The first value is the value of x, and the second value is the value of the function. So for point of inflection, we need to put this obtained value of x 0 and this given equation. y, x cube minus 3x plus 3. So put x equal to 0 in this equation to get y is equal to plus 3. So therefore point of inflection is an ordered pair x comma y, and x is 0, y is 3. So that is the required point of inflection. Now the last topic which is being studied here, that is Lopital's rule for 0 by 0 form. Remember that whenever a limit is in 0 by 0 form, or we may say that infinity by infinity form, we will apply Lopital's rule there. Now what is Lopital's rule? For example, this is a limiting value of this rational function f of x divided by g of x. Whenever you apply this limit on f of x and the answer is 0, and whenever you apply this limit on g of x and the answer is 0, so that will become 0 by 0 form. Then L'Hopital's rule say that find the derivative of above function and find the derivative of below function and then apply the limit. If again there is this form is 0 by 0, then again find the second derivative of this function and second derivative of this function until this form disappears and you are able to find the limit of the function. So that is the criterion for 0 by 0 form of a limiting value of a function. That is the most simple rule, L'Hopital's rule. Remember that for 0 by 0 form or infinity by infinity form, we factorize numerator and denominator or rationalize them if possible, but this rule simplifies the work. That is the most simple work to find the limiting value of a rational function whenever that rational function is in the form 0 by 0 or infinity by infinity. So here is an example. Find the limit of this rational function. We see that whenever we replace x by 2 here, we'll get 0 upstairs, and whenever we replace x by 2 here, so we'll receive 0 in the denominator as well. So this is 0 by 0 form. Then the previous topics, we factorize this numerator and then cancelling like terms to vanish this 0 by 0 form. But now in this sense, we will apply L'Hopital's rule to find the limit of this 0 by 0 form of the limit. Now what is the criterion? We need to find the derivative of above function and below function. So that is the derivative of above function and this is the derivative of below function. Now what is the derivative of x square? That is 2x, and derivative of 4 is 0. Similarly, derivative of x is 1 and derivative of 2 is 0. So that is, we obtain here derivative of x square is 2x and 4 is 0, and derivative of x is 1 and derivative of 2 is 0. So that is limit x tends to 2x by 1. Now here if you replace x by 2, we will get 2 2s are 4, and that is the limiting value of this rational function. So this is how to apply L'Hopital's rule. Now we see here, if you find the limit of this function, we know that limit x approaches to 0, sin x by x equals to 1. We know this formula. But if you see here, if you replace x by 0 in numerator, then sin 0 is 0, and if you replace x by 0 here, so that is again 0 by 0 form. Now using the criteria of L'Hopital's rule, find the derivative of above function and derivative of below function. Derivative of sin is cos and derivative of x is 1. Now cos of x by 1 is actually cos of x. Now if you replace x by 0 here, so that will become cos of 0, and we know that cos of 0 is 1. Now you see here that this is very simple approach to find the limiting value of a rational function, which is in 0 by 0 form. Again, we can apply Lopital's rule for infinity by infinity form as well. Just look at this example. Evaluate this limit. Limit x approaches to infinity e power 3x by x square. Whenever you replace x by infinity here, so 3 into infinity is infinity, and e power infinity is infinity. And whenever you replace x by infinity here, so infinity square is again infinity, so this is infinity by infinity form. We can apply Lopital's rule here as well. And what is that rule? Find the derivative of numerator and derivative of denominator as well. Derivative of e power 3x, we know that that is 3 into e power 3x, and derivative of x square is 2x. Now again, if you replace x by infinity here, so e power infinity is infinity, and this whole numerator will become infinity. And whenever you replace x by infinity here, so 2 into infinity is infinity, and denominator is again undefined. So that is again infinity by infinity form. 3 by 2 is constant, so that's why we write 3 by 2 outside this limiting value. And this is again infinity by infinity form. So what should we do? We need to find the derivative of numerator and derivative of denominator. So that is the derivative of numerator, and this is the derivative of denominator. Now derivative of e power 3x is again 3 into e power 3x, and derivative of x is 1, so that is 1. Now writing this 3 outside here, so 3 3s are 9, so that is 9 by 2, and that is e power 3x. Now we are able here to replace x by infinity here, because this is not a rational function, that is an exponential function. Replace x by infinity, and e power infinity is infinity. Infinity into something is infinity. So this the limiting value of this rational function is undefined infinity. So that's how we apply Lopital's rule to find the limit of a function, rational function, which is in the form 0 by 0 or infinity by infinity. This rule is very important with respect to any examination point of view. So try to learn and practice those questions regarding Lopital's rule.